Welcome to the exercises for DGD 3, which deal with some questions on induction and then some stuff on propositional logic. So starting with the induction question, 2.3.1, it's got a few statements which we're going to be proving. The first one is that for all natural numbers k, the natural number k cubed plus 2k is divisible by 3. So since it's a proof by induction, we can say it's a proof by induction. And we can start with a base case. Because it's over all natural numbers, our base case is the smallest natural number, which is 1. Then all we have to say is look at our expression when k is equal to 1. This is 1 plus 2, which is 3, which we can write as 3 times 1. This means that it's a multiple of 3. So this implies that 3 does divide k cubed plus 2k when k equals 1. For the inductive step, we should start with our inductive hypothesis, which is to let k be greater than or equal to 1, always greater than or equal to the base case, and assume that 3 does divide k cubed plus 2k. So we let k be greater than or equal to 1, and we assume the result at k. We're going to work towards proving it for k plus 1. So first, unpacking this assumption, this means that there exists an integer j such that k cubed plus 2k is 3j. And now we want to consider the next case, which is the expression at k plus 1. Note we're not making any claims here yet, we're just considering this expression. We can expand this. As follows. And we can regroup our terms, and in regrouping our terms, our goal is to use this assumption about k cubed plus 2k. So we'd like to keep this k cubed and this 2k together. So I'm going to group those. And otherwise, I'm going to leave everything else on its own. 1 plus 2 is 3. Now this k cubed plus 2k we can replace with 3j. By assumption. And now there's a common factor of 3 on all terms, which we can factor out. Then we can say, since j plus k squared plus k plus 1 is an integer, since all of its pieces are integers, this means that 3 divides this expression that we considered, which is the expression at k plus 1. So we assumed the result was true at k. From there we were able to prove that it's true at k plus 1. Hence, by induction, the result holds for all k. Part 2 is a similar statement. We're going to prove that for all natural numbers k, this expression is divisible by 4. The proof follows the same format. By induction, we consider the base case, which is still k equals 1, the smallest natural number. And there we just have to consider this expression when k is replaced with 1. This is 1 minus 6 plus 11 minus 6, which is 12 minus 12. So we get 0, and 0 is a multiple of 4. It's 4 times 0. So this implies that 4 divides our expression when k is equal to 1. Now for our inductive step, we let k be greater than or equal to 1 and assume that 4 divides the expression at k. This means that there exists an integer j such that our expression is 4 times j, because we've assumed it's a multiple of 4. That's what divisible by 4 means. Now we would like to consider the expression at k plus 1. Which is somewhat long-winded, but this is the expression we're considering, and we can expand all of this. This is the expansion of k plus 1 to the 4th. We get 6 times k plus 1 cubed, which ends up being this. Plus 11k squared, k plus 1 squared. And minus 6 times k plus 1. When we simplify this and gather like terms, we would like to find a copy of our original expression at k, because this is what we have an assumption about, so we would like to isolate that. So we can write this as our original expression, taking k to the 4th minus 6k cubed plus 11k squared and minus 6k. And the rest we can group together as like terms. So there's just one cubed term remaining. Otherwise we get 6 minus 18 is negative 12 k squared. Then we get 4 minus 18 is negative 14, plus 22 is 8. The minus 6 is already used, so 8k. And for constants, we get 1 minus 6 is negative 5, plus 11 is 6, minus 6 is 0. So we just get this. Now we can replace this, because we've made an assumption about it. We've assumed it is 4j. So this is 4j plus 4k cubed minus 12k squared plus 8k by assumption. And now everything here has a factor of 4, so we can just factor that out. And we get this. And now j plus k cubed minus 3k squared plus 2k. This is an integer because all of these things were integers. So we have that our expression at k plus 1 is 4 times an integer. So this means that 4 divides our expression at k plus 1, which is written out like this. That concludes the inductive step, and so hence, by induction, 4 divides the original expression for all natural numbers k. The third statement is that for all natural numbers k cubed plus 5k is divisible by 6. We'll approach it similarly by induction. Our base case is again k equals 1, where 1 cubed plus 5 times 1 is 6, which is 6 times 1. Therefore, this is divisible by 6. So 6 divides k cubed plus 5k when k is equal to 1. For the induction step, we let our variable be greater than or equal to our base case, and we assume that 6 divides our expression at k. This means that there is an integer j such that k cubed plus 5k is 6j. And now we want to consider the expression at k plus 1. We can expand this. And we can group it together, isolating for the expression at k that we have an assumption about, and then grouping all other terms. We can replace this with 6j by assumption. However, now we reach a problem. Before, we had nice factors. Our factor of 4 or a factor of whichever would come out of all terms, but a factor of 6 does not come out of all terms. So we would like 3k squared plus 3k to be divisible by 6 for all k. So we can make a claim of what we'd like. I'm going to switch variables to keep track of things. Our claim is that 3n squared plus 3n is divisible by 6 for all natural numbers n. And in order to use this claim, we need to prove it. And so we can write a proof also by induction. So the base case is n equals 1. And we can see that when n equals 1, this is just 3 plus 3, which is divisible by 6. Concluding our base case. For our inductive step, let n be greater than or equal to the base case, which is 1, and assume, I'm just going to write it in this form immediately, that there exists an integer L such that 3n squared plus 3n is 6L. This is the same as assuming this is divisible by 6, it's just immediately writing it as it is a multiple of 6. So now we're going to consider the expression at n plus 1. This can be expanded. We can group together the expression that we've made an assumption about, 3n squared plus 3n, and everything else is 6n plus 6. The expression we've made an assumption about we can replace with 6L. And now a nice factor of 6 comes out of everything. So since this number is a multiple of 6, this means that 6 divides this number at n plus 1. So we can say that concludes the inductive step, and so hence, by induction, 6 divides 3n squared plus n for all natural numbers n. So now, since we've proven this, we can use the fact that 3k squared plus 3k is divisible by 6. So we can say this implies that there exists, I'll use L again, an integer such that 3k squared plus 3k is 6L. And so we can take our expression up above, which is 6j plus 3k squared plus 3k plus 6. This expression that we were working on is equal to 6j plus 6L plus 6, since we now know that this middle part is divisible by 6. So we can factor the 6 out. J plus L plus 1 is an integer, so we have that our original expression is 6 times an integer. So this implies that 6 divides the original expression we were working on was this at k plus 1. That concludes the inductive step. So by induction, 6 divides k cubed plus 5k for all natural numbers k. So it's not always the case that after you expand into the inductive step, you get something which is clearly has the properties you want. You may have to prove that some smaller part of it has the property you want by some other method. Here, another proof by induction worked. Next up is exercise 2.3.3, which is to prove that for all integers greater than or equal to 2, we have that k squared is strictly less than k cubed. This we can also prove with induction. So proof by induction. Our base case now is the smallest integer to which we want our statement to apply, which is now going to be 2. And then we get the statement that k squared is 4, k cubed is 8, and clearly 4 is strictly less than 8. So this holds in the base case. For our inductive step, we let k be greater than or equal to the base case, which is 2 in this example, and we assume the statement at k. So we assume that k squared is less than k cubed. This means, by definition, that k cubed minus k squared is natural. Now, since we want to work towards this expression at k plus 1, I'm going to consider k plus 1 cubed minus k plus 1 squared. By showing that this is natural, we can then conclude that k plus 1 cubed is larger than k plus 1 squared. So first, we can just expand this. To get the following. And we can regroup it like this. Because we've made an assumption about k cubed minus k squared, we know it's natural. Then we can gather together the other terms. So we have a 3k squared, we have 1k, and the plus 1 and minus 1 cancel out. So we get this expression here. And we can say that this is natural by closure, since k larger than or equal to 2 implies that k is natural. And so 3k squared plus k is natural under closure by closure of multiplication and addition. And k cubed minus 2k squared is natural by assumption. So k plus 1 cubed minus k plus 1 squared is a natural number. Therefore, k plus 1 squared is strictly less than k plus 1 cubed, which means the result holds in the k plus 1 case. So by induction, overall, k squared is strictly less than k cubed for all integers k which are greater than or equal to 2. Exercise 2.4.1 is to prove proposition 2.35. This statement is important to the definition of greatest common divisor, which we'll see later. And the statement is that suppose we have two integers, a and b, which are not both 0. Then the set S, which is defined to be natural numbers of the form ax plus by, for some integers x and y, is non-empty. So to prove that a set is non-empty, we can demonstrate that it contains at least one element. So that's what we will do. And we're going to begin our proof with a without loss of generality. And I'm using this to say, without loss of generality, assume that a is not equal to 0. We know that these are not both 0. So if a is not equal to 0, this is fine. We're not adding anything new. If a is 0, then b must not be equal to 0. So just rewrite this with b, is what this means. One of them has to be not 0, so we're going to pretend it's a. Now we would like to build an element of S, which means we just need a times x plus b times y, and that the result is natural. So since a is not equal to 0, this implies that there are two cases. Either a is natural, or the additive inverse of a is natural. So case 1, assume a is natural. Then a is equal to a times 1 plus b times 0. b times 0 is 0, a times 1 is just a, so we get this. But this is of the form a times an integer plus b times an integer, and it's natural. So since it's of the form required by S and is natural, which is also required by S, it's an element. So this implies that a is an element of S, and since it has an element, S is non-empty. Case 2, assume that the additive inverse of a is natural. Then we can write that the additive inverse of a is a times negative 1 plus b times 0. A times negative 1 is the additive inverse of a by propositions in previous chapters. And adding b times 0 doesn't change anything. And so again, this is natural by assumption, and it follows the form of a times an integer plus b times an integer, where the result is natural, which is exactly what's required by S. So this means that negative a is an element of S, and since it contains an element, this means S is not empty. So in either case, we concluded that S is not the empty set. Therefore, S is not empty in general. Concluding the proof. 3.1.1 gives us 5 statements in English and asks us to express them with quantifiers. So we'll go through them one by one and write out the translation. Number 1 is there exists a largest integer. So this is going to be an existence statement. So we can say there exists an integer a such that this is the existence statement. Largest is a comparison to all other integers. So for all integers b, a is greater than or equal to b. There exists an integer which is bigger than all other integers. This is the idea of largest. Similarly, there exists a smallest natural number, is that there exists a natural number such that smallest is a comparison to all other natural numbers. So for all natural numbers m, n is less than or equal to m. 3 is the statement that every integer is the sum of 2 integers. Every means for all. So every integer is for all integers a. Now is the sum of 2 other integers means that there exists 2 other integers which add to a. So there exists integers b and c such that a is b plus c. 4, every integer is the square of an integer, is very similar. Every integer is for all. So for all integers a, it is the square of some integer, which means that there exists an integer b such that a is equal to b squared. And finally, 5 states that the equation x squared plus 5y cubed equals 4 has a unique integer solution. This is an existence statement. It has at least one and exactly one solution. So exists unique is expressed with the existence quantifier and an exclamation point. So this means there exists a unique pair of integers, x and y, such that this equation is satisfied. So that's how all of these would be translated. 3.1.2 gives us 5 quantified statements and asks us if each is true or false. So we'll go through, say whether it's true or false, and give an explanation. The first says that for all integers x, there exists a y, which is another integer, such that x plus y is equal to 2. An important thing to remember when reading such statements is that variables which are introduced later can depend on variables which were introduced first. So here, y gets to, in some sense, know what x is before it's chosen. So this ends up being true. And it's true since if x is an integer, the exists y just means there needs to be at least 1. So we can choose y equal to 2 minus x. Then x plus y is x plus 2 minus x, which is 2, as we want. So this is true. Given knowledge of x first, we can pick an appropriate y so that x plus y is 2. Part 2 says for all integers x, there exists a natural number y, such that x plus y is equal to 2. This is false, because now when y is restricted to the natural numbers, we might not be able to choose 2 minus x, because 2 minus x may not be natural. So for instance, to show that this is false, we simply need to provide a counterexample. And for the counterexample, we can let x be 3. Now, no matter which y we pick, because we have to pick a natural number, it's not going to be equal to 2. So then, since y must be natural, y is greater than or equal to 1. And this means that x plus y is greater than or equal to 3 plus 1, which is 4, which means that x plus y cannot be 2. So there is no natural number you can add to 3, which will give you 2. Therefore, this statement fails for 3. Because it does not hold for all, it is false. Statement 3 is similar to statement 1, but the order of the quantifiers has been swapped. Now the existence starts first, and the for all comes later. And that swapping makes this false. If this were true, it would mean that there is one natural number x, such that x plus anything is 2. So by contradiction, if such an x existed, then x plus anything would be 2. So in particular, x plus 0 would be equal to 2, and x plus 1 would be equal to 2. But x plus 0 is just equal to x, so this means that x is 2. So therefore this equation implies that 2 plus 1 is equal to 2, which we know is a contradiction. So since such an x existing implies a contradiction, no such x exists, and therefore this is false. Part 4 claims that there exists an integer a, such that for any other integer, a plus b is equal to b. So because there's b on both sides here now, this ends up being true. There is one integer that we can pick such that anything you add to it, it doesn't change. It just a plus b is b, because we can choose a to be 0. Then, since a is chosen to be 0, for all other integers, a plus b is 0 plus b, which is b as desired. So this is true. Part 5 swaps the order. Instead of choosing a first, we're given b first, and then we have to choose a. Previously, when we swapped the order of two statements, it ended up changing the truth value, but that is not always the case. Here, this is also true. Since the for all b clause comes first, we are now given b with no control, and then we get to pick a. Here, we had to pick a, and then it had to work for all b. And so this is a demonstration of how the order matters. So because b comes first, we can say given an integer b, we can choose, and the same choice works. A equal to 0, then a plus b is 0 plus b, which is b as desired. So this is true. Throughout these 5 expressions, you've probably heard me using the language, whenever there is a for all, it's given, sort of chosen without our control. Whenever there is an existence, it's something that we can choose when we're making our argument. Because there just needs to be one, our choice, if valid, is at least one. So this is something to keep in mind. Things quantified by a for all, you sort of have to treat like variables because it has to work no matter which possibility it is. And things quantified by an exist, you can make some choices and you can specify because you just need there to be at least one. 3.3.1 gives us 7 expressions to negate, some of them written out mathematically, some of them in English. We're going to identify the underlying logical structure and then come up with the negation. So 1, every polynomial has a real root. Every is a for all statement. So the negation becomes an existence statement. So the negation is that there exists a polynomial and then the negation of the claim. So there exists a polynomial that has no real root. Or that does not have a real root, whichever way. For 2, Steve is blonde and Samantha is tall. Importantly, the logical part here is the and. Therefore, its negation, this switches to an or, and the other parts become negated. So its negation, Steve is not blonde. The negation of Steve is blonde, or, and then the negation of the last part, or Samantha is not tall. For 3, it's written out in symbols, so it's sort of easier to see what happens when the negation occurs, except for this uniqueness. Exists unique is sort of 2 claims. It claims that there exists one, and it claims that if 2 things have the same property, then they're actually the same. So this first can be rewritten as for all x, which is an integer, first the existence, there exists a y such that x times y is equal to 3. That's the first part. And the second part, the uniqueness, is that for all y1 and y2, which are integers, xy1 is equal to 3 and xy2 is equal to 3 implies y1 is equal to y2. So this is much more long-winded, which is why we have this symbol exists unique. But it's just, given x, there is a y such that xy is equal to 3. And also, anytime 2 different y's have this property, they're actually the same, which means that only one has this property. Therefore, its negation becomes there exists an integer x such that for all y, xy is not equal to 3. This is the negation of there exists y such that xy is 3. The and becomes an or. And then here we have the all becomes an existence. So there exists y1 and y2 integers such that the negation of an implication is the first part stays the same. You get an and the last part gets negated. So such that xy1 is equal to 3 and xy2 is equal to 3 and y1 is not equal to y2. The way we can understand this long negation, the original statement claimed that for all x, there was only one y, such that x times y is 3. The negation then is either there's no y, or there's more than one y. This portion here is there's no y. For all of them, it doesn't work, so there's no y. Or this portion here is that there's more than one y. There's two y, they both do it, and they're not equal. So this is the negation of this. Onto a simpler example. That cow is neither large nor pink. This is an and statement. It's not large and not pink. So its negation becomes the opposite of not large, which is large, and the opposite of not pink, which is pink. So the negation, that cow is large or pink. Here we have an if statement. If f of xy is greater than 0, then x is greater than 0 or y is less than or equal to 0. There are variables here, and so this is understood as a for all statement. So this is equivalent to for all xy. If f of xy is an implication, so f of xy greater than 0 implies the conclusion. X is greater than 0 or y is less than or equal to 0. So the negation of this, which we're just going to write out, because of this implied or this assumed for all in front, this understood for all, the negation becomes an existence. So there exists x and y such that. Now the negation of an implication is the first part stays the same. So such that f of xy is greater than 0. The implication becomes an and we get the negation of the conclusion. So the negation here is the negation of this piece. So x is less than or equal to 0, or becomes and the negation of this piece, y is strictly greater than 0. And this is the negation here. For 6, it's an if and only if statement. The quotient group G mod n is finite if and only if G is finite. If and only if means that the truth values of these match. So the negation would therefore be the truth values not matching. So what this ends up looking like is negation. We'll start with the quotient group G mod n is finite and G is infinite. So one staying the same and the opposite of the other because they will not match. Or G mod n is infinite and G is finite. These are saying that they're either both finite or both infinite, so the negation is therefore the two cases that either one is finite and the other is infinite, or the first is infinite and the other is finite. Lastly, this is just a pretty straightforward quantified statement, but written in English. For each corresponds to for all, so the negation of a for each is a there exists. So there exists L in n, such that there exists n, the negation becomes a for all statement. So for all natural numbers n, and then the last piece just gets negated. So xn is less than or equal to L. And so this is the negation. One way that might help to think about negations is that the negation of a statement simply describes all the possible ways that the statement could be false. So if something has to hold for all elements, it fails as soon as one doesn't have the property. That's why it becomes a there exists. And if at least one has to have a property, then it fails if all of them don't, which is why exist becomes for all. So negations just describe all the possible ways that the original statement could be false.